Hello everyone, welcome to lecture 2 of Robotics and Automation. In the previous lecture, we had an introduction about robotics. And especially if you remember, we talked about different types of joints, and then we talked about different types of industrial robots, and we also talked about some advantages and disadvantages of robots, and finally we talked about safety related to industrial robots. In today's lecture, we shall talk about configuration space. We shall see what is a configuration and what is a configuration space and how it is useful for industrial manipulators. And after that, we shall learn about degrees of freedom of the robot. We shall see degrees of freedom of a rigid body and how we can calculate it. And then after that, we shall learn that how we can calculate the degrees of freedom of a robotic arm. There is a mathematical formula, and we shall try to apply this formula to calculate degrees of freedom. And then after that, we shall talk about configuration space topology and its representation. And finally, we shall end this lecture with a brief introduction about task space and workspace. So this is today's agenda, and let's begin. Before beginning and going into detail, I want to inform you that if you want more reading about all these topics, so I shall recommend this book. The book name is Modern Robotics, and its chapter is chapter number 2. So there you can find more details and more examples about today's lecture. So let's begin. So firstly, we have to define what is configuration. What is a configuration of a robot? And here we are talking about industrial robots, industrial robotic manipulators, you can call it. So a robot's configuration is a specification of the position of all joints of its all joints. I think that will be proper. So if you have, let's say you have a 2-link robot, here I draw it like this. So here you have a fixed base, and then you have a joint, and then you have this link 1, and this is your second joint, and this is the link 2. So what the definition of the configuration, robot's configuration, so it says that the specification of the positions of the joint. So we have to specify the position of joint 1. This is J1 and J2. So how we can specify the position? Of course, this is because it can only rotate. So this is only angular position, and this can be specified by angle theta 1 and the joint 2 by theta 2. So it means that if we have specification of theta 1 and theta 2, this corresponds to a specific configuration of this robotic arm. Let's say if theta 1 is equal to 45 degrees and theta 2 is equal to 45 degrees, then a robot will have a configuration like let's say like this here. Should I draw it here? Yeah. For 45 and 45, the robot should have a configuration something like this. Sorry, this is theta 2 and this is theta 1. So this is one configuration of your robotic arm. But if you change this angle, if you let's say make the theta 2 dash, if you make theta 2 is equal to let's say 60 degree, then your this link will move somewhere like here, and now you will have a different configuration of your robotic arm. So here we have learned what is the configuration of a robot. If this is clear, then we can now move toward the configuration space. So what is configuration space? Configuration space is the n-dimensional space containing all possible configurations of a robot So all possible configuration of a robot, which means that it is a n-dimensional space. N is the number of, you can say number of joints, in the robot. And let's say for a 2D robot like this, this is here joint 1 and this is joint 2, and this is here, I call it theta 1 and then theta 2. So for a 2-link robot, the n will be 2. Okay, so now we have to plot all possible configurations, so all possible combination of configurations. So let's draw a space, a 2D, because it's a 2D, 2 joints, so it will be a 2D space. So here will be your theta 2, here will be your theta 1, and it has all the values starting from 0 to, let's say here we have 45, and then here you have 90 degree, and here you have again 45, and here you have 90 degree. So this space containing all possible configurations of this robotic arm, this is called the configuration space. For one particular configuration, let's say if we have theta 1 is equal to 45 degree and theta 2 is equal to also 45 degree. So for this particular configuration, if we map this configuration into our configuration space, it will lie somewhere here. So for this particular configuration, the point in the configuration space is somewhere here, where theta 1 is also 45 and theta 2 is also 45. Okay, I think it's confusing, so let's not draw it. And similarly, if you have other values, so let's say if you have theta 1 is equal to 45 and theta 2 is equal to 60 degree, then it means your point will be, for this configuration space, for this configuration, your configuration space will have a point somewhere here. So yeah, so this is how this is called configuration space, and it has all possible configurations, okay, from theta 2 0 to 90 and theta 1 also 0 to 90, all possible combinations of theta 1 and theta 2. I hope that this is clear now. So if this is clear, now we can move forward, and let's see, description of configuration of a door can be done by a single coordinate theta. So moving away from robots, let's see how we can define the configuration of a common real world objects. And here we are taking the example of a door. So a door, how can we define the configuration of the door? So first we need to see where the movement is happening. So let's say this is so let's say this is a door here. So and so how we in which axis it has motion? So of course it's rotating about, let's say, z-axis. So here you have z-axis, and let's say this is your x-axis and this is your y-axis. So of course it's rotating about z-axis. It's open like in this way and then close this way. So we can describe its motion by angle theta here. So it has, because it has only one motion, so for its configuration only one variable is required. So yeah, so its configuration space will have only one variable, and that will be theta is equal to 0, 1, 2, 3 and so on up to 90, or you can say maybe less than 360. So this is how we define the configuration and the configuration space of a door. Now another example is a point in a plane can be represented by two coordinates x and y. So let's see, when we have a point in a plane, how can we describe its configuration? So this is our plane, a 2D plane. And so here we have, this is x-axis and this is y-axis, and so the point is, let's say, somewhere, point is located here. So a point means its dimension is, we can ignore its dimension, so it's just a point. It's not a circle, it has dimensionless point. It's a dimensionless object, you can say. So to describe its position in a 2D space, we need two variables: its position along x-axis and its position along y-axis. So now we have two, it means its configuration is dependent upon two variables. X and Y dependent, and its configuration space, okay, will look like something like this, and you can say where you have values of X from 0 to up to so on, and there you define its configuration. Okay, now let's see a third example. A coin laying on a table can be described by three coordinates. So here we have, let's say here we have a table, and we have a coin on this table, let's say here. So this is a coin, and this is a green is a table. And now to describe its configuration, so again I would like to compare. The configuration is a specification of all the position of the joints. This was for robot, but for a common object like this coin or this point, we can call it like configuration is a specification of all positions and or orientations. Okay, so how can we specify the positions and orientation of this coin? So to specify the position, we need X and Y, and to specify the orientation we need theta. And now you're wondering why we ignored here the theta in the configuration, why theta is not included. Because this was a dimensionless object. So here it doesn't matter which direction it rotates, so theta is not necessary here. But once the object is it has dimensions, so then we cannot ignore theta. We need to specify its orientation also. So all the position can be represented by two variables, which is X and Y, and the orientation can be represented by theta. So we can define here X is the position along X-axis, position along Y-axis, and then you can also define an angle theta with positive X-axis. So this is how you define the configuration, and this whole combination of all possible positions and orientations. So this space, it will be a configuration space of your coin. So the next time if the coin is, let's say, moved here, it will have a different configuration. It will have a different X, Y. So let's say if your coin moved here at position 2, so this time it will have a different configuration, because it will have a different X and Y coordinate, and also it may have a different orientation. So yeah, so that's how we define the configuration and configuration space of objects and also robotic arms. Okay, so we have seen the configuration space, and once it's clear, now we can move to degrees of freedom. So what are the degrees of freedom? We already had introduction in the previous lecture, so here we shall try to go in the detail. So one definition says that the minimum number of real valued coordinates needed to represent the configuration is the number of degrees of freedom. So the important things in this definition are minimum number of real valued coordinates. So here we need some coordinates to represent the configuration. So the coordinates to represent configuration is the degrees of freedom. For example, in the previous, okay, the example will come here. This yeah, the third point. So before moving to the example, we see another definition of this degrees of freedom. The number of degrees of freedom of a robot is the smallest number of real valued coordinates needed to represent its configuration. So this one is specifically for robots, and I think the definition is same. They have same meaning. Okay, so here let's see example for an object. A door has 1 degrees of freedom. Why a door has 1 degrees of freedom? Because we have seen that in the previous example that door can be represented, the configuration of a door can be represented by one angle theta. Okay, so this is its configuration. So now if door can be represented by theta, okay, so the definition of the degrees of freedom says that the coordinates needed to represent the configuration is the number of degrees of freedom. So it means if your door can be represented by 1 coordinate, so it means that its degrees of freedom is 1, because it can be represented by one coordinate. Its configuration can be represented by 1 coordinate, which is theta. And let's say another example, a coin laying on the table has 3 degrees of freedom. So in case of coin, we have it can be represented by 3 coordinates. Its configuration can be represented by 3 coordinates, x, y, and theta. So it means it has 3 degrees of freedom. If you want to visualize it, a coin, it can move along x-axis, it can move along y-axis, and it can also rotate about z-axis. Okay, so z-axis, let's say, is coming here. So this coin has 3 degrees of freedom. Okay, Let's see another example. Should I mention here, I think the colors, I made the coin with a different color, so it's okay. So yeah, so this is red color is a coin, and it can move along x-axis, which is 1 degree of freedom. It can move along y-axis, which is a second degree of freedom, and it can move along z-axis with angle theta, so it has third degree of freedom also. But in case of door, it has only one configuration, so it has only 1 degrees of freedom. It can only rotate. Now let's see the third example. Okay, third example is not written here, but we can see the degrees of freedom of a two-link robotic arm. I think so we shall cover this topic in the next slide, so then it will be repetition. So we can okay, so till here I hope that you understood the concept of degrees of freedom and how we can calculate the degrees of freedom of different objects. So first you need the coordinates that are being used to represent its configuration. So the configuration is the specification of its position. So once you have the coordinates, so the number of coordinates you needed to represent its configuration are the degrees of freedom. So for door it was 1, and for coin it's 3. And yeah, we can take one more example. For example, the point. A point in a 2D plane. So what will be its degrees of freedom? So let's draw it here. So this is x-axis, this is y-axis, and here we have a point. So what will be its degrees of freedom? So first we need to define how many configurations it has, how many coordinates we need to represent its configuration. So we have already learned that for a point we can represent its position, or we can specify its position using two coordinates x and y. So its configuration can be represented by two real valued coordinates x and y. So it means its degrees of freedom are 2. So yeah, I hope this is clear. What are the degrees of freedom and how we can calculate it. In the next slides it will become more clear that how we can calculate the degrees of freedom of more complex objects, for example robots or in 3D objects. So now we try to calculate the degrees of freedom of a little bit more complex scenarios. So okay, let's see an example. We shall take the same example as we did in the previous slide. 2D coin, or a coin in a 2D plane. So let's imagine that we have a plane here, So let's imagine that a coin, it's laying on a tabletop, and from the top view we can consider this table surface as a 2D plane. Okay, and here we have x-axis and y-axis, and here we have a coin on this surface. Okay, let's make it a little bit bigger. So this is a coin we have. So what next we have to do is we have to take 3 points A, B, C on the coin. Just to make it clear that why we are doing it. So we want to find the degrees of freedom of this coin that is laying on the tabletop. In the previous slide, we by looking, we said that it has 3 degrees of freedom. We said, okay, it can move along x, y axis, and it can also rotate. So 2 displacements and 1 angular movement, so 3 degrees of freedom. But now in this slide we are going to make a systematic method that helps us to find the degrees of freedom of objects for complex environments. For example, in a 3D or more complex objects that are not just simple, or in a 2D. So using this example, we shall make a systematic method by which we can find the degrees of freedom of complex objects or objects in complex dimensions. So the next step is take 3 points A, B, C on the coin. So we take these 3 points. Let's say this is point A, this is point B, and here we have point C. Now what we have to do is to attach a coordinate frame to the plane, so that we already have attached this frame xy coordinate. Okay, so now what we have to do is to, at the center of okay, let's make this point a little bit. Okay, this one here. Okay, so now what we have here is this distance from A to B. This distance we can name it as DAB. Okay, and the distance between B to C, we can call it okay, first, before this, we just want to, this distance between A and B is DAB, so it means that point B will always be at a fixed distance from A. It can, so this, you can say that this is the radius of a circle around, and the center point of this circle is A. So the center point of the circle is A, this black circle, and the radius is DAB, and B is on the circumference of this circle. Now we have to measure the distance between point B and C, and we can say that this distance is dBc, a straight line. And again, for this also, taking B as a center point of the circle and dBc as a radius, we can again draw a circle that having this center point B. So how can we do that? We can just draw this circle, or maybe to make it better, we can use this option ink to shape. And same we can do for point A. I don't know why it's not drawing. Okay, sorry. Ink to shape. Okay, so if we have done this far, it means we can also draw a blue circle. Okay, so this blue is the coin, and we have taken 3 points A, B, C, and then we have drawn a circle with center A, and then we again draw a circle with center B, which is the green one. And now what we have to do is we have to again draw a circle with center DBC, and also with this center DAC. So now let's take another point, another distance, which is the distance between A and C. We call it DAC. Okay, and now we have to draw one more circle that has a center A, but it has a radius DAC. So we can draw it like this. Yes, so at the center should be at point A, and its radius should touch point C. So yes, so now we shall write here, this line represents the coin. Okay, and the other colors, they represent the circles with the radius, corresponding radius or the distance that is given here, DAB, DBC, DAC. So if we want to, let's say, calculate the distance of these points, these between these points, so we can use the formula like this. We can say that DAB is equal to XA minus XB square plus YA minus YB square. And similarly, we can calculate the distance DBC XB minus XC square plus YB minus YC square. And the third distance is DAC. XA minus XC square plus YA minus YC square. So this is how we can calculate the three distances, and the XA, YA are the X and Y components of point A, and corresponding other coordinates of the points are given by their subscripts. So we can calculate this distance, and now what we have to do, we have to derive a formula for degrees of freedom. So what we have here, we have realized using this basic example, this blue color is a coin, and we have taken 3 points A, B, C on the coin, and then what we did, we said that okay, only a point, if there is only a point, let's say a point in a 2D plane will have how many degrees of freedom? Only point A will have 2 degrees of freedom, which is X and Y. So if we add point B at a distance of DAB from point A, then point B will have how many degrees of freedom? Here now you see. So the thing is, we only point A has 2 degrees of freedom, but if we add B also along with point A, so now what will happen, we have a constraint here, because the point B must be at a distance DAB from point A. So this is a constraint. What is a constraint? Constraint limits the motion of a point of a body. Okay, so example of constraint is that should I draw it here? Okay. An example of constraint will be, let's say, here we have a link, and here we have a joint, and this joint is Revolute Joint. So it means it can rotate. This link can rotate with angle theta. So it means it has 1 degree of freedom. This link can rotate about this joint because this is a revolute joint. So it has 1 degree of freedom, but it cannot move along x-axis, y-axis, or it cannot move along x-axis. So this cannot happen. Let me change the color. So it cannot move along y-axis and it cannot move along x-axis, the linear motion. Why? Because here we have a constraint, and this constraint does not allow any linear motion. Okay, it only allows circular motion. So here we have actually 2 constraints. In this example, there are 2 constraints and 1 degree of freedom. So it means that constraint limit the motion of a body or of a point, and it also limits the degrees of freedom. So if you see that B must maintain a distance of DAB from the point A, so point B will always be here because coin is a rigid body, and in a rigid body, because rigid body is not a flexible body, it's a hard metallic body, you cannot bend it, you cannot change its shape. So that's why the distance between point A and B, it will never change, it will always remain constant if it's a rigid body, if we consider coin as a rigid body. And that's also important here to mention. We consider coin as a rigid body. So the distance between points is constant. Okay, so this distance will always be constant. It means B can be here, here, anywhere along this dark circle. It can have any position, but it cannot go outside of this circle, and also it cannot go inside of this circle. It must be, okay, it must be on the circumference of this dark circle because it has a constant radius. So it means that we have 1 constraint here. This DAB is 1 constraint. Okay, so if this is a constraint, it means this point B can only have 1 type of motion, and this is a circular motion along the circumference of the circle. So this point B has only 1 degree of freedom, which is you can call it the angle theta because it's circular motion. So point B point B will have 1 constraint, which is DAB, which is a radius, and 1 degree of freedom, which is theta, the rotation. Here we can write down theta also, so very small. I hope this is clear for till now. Point A has two. Point A can move anywhere because there are no constraints, and for point B we have one constraint and one circular motion, so it has 1 degree of freedom. And now let's see what was the first one. Only point will have 2 degrees of freedom. I think I forgot to write here point A. Okay, only point A will have 2 degrees of freedom and 0 constraints. If we add point B at a distance of DAB from point A, then point B will have one constraint, which is the radius of circle, and 1 degree of freedom, which is the rotation. Now let's talk about point C. Point C must be located at a fixed distance from point B, and the distance is dBc. And this point C also must be located at a fixed distance from point A, which is distance is dAc. It means that point C must lie on the green circle, the intersection of green circle and red circle. Red circle has a radius of dAc, and green circle has a radius of dBc. So point B must lie at the intersection of these two circles, as you can see here, and it means that point C has two constraints, which is dBc, dAc. And how many degrees of freedom it has? No, because it cannot move. It cannot move because if it moves like on the circumference of red circle, then it's no longer on the intersection of circle green and red circle. Okay, so point C must be lie at the intersection of these two circles. So it has no degrees of freedom and has two constraints. So let's add, like, if we add another point which is point C, along with point A and point B on the coin. So what will happen? this point C will have two constraints and 0 degrees of freedom. Okay, so yeah, and similarly if you add more points on this coin, okay, it will also have 0 degrees of freedom, because there will be more constraints, okay, than degrees of freedom. So any other point you add, let's say a point D, it must be fixed with respect to point A, B, C at a constant distance, and so it cannot move anywhere. So there is no point of adding, there is no reason of adding more points, because we already know that its degrees of freedom will be 0. Okay, so only these 3 points are useful. That's why we took these 3 points, A, B and C. Now what we have learned in this with these 3 points is that point A, because it's when alone, point A will have 2 degrees of freedom, as we have learned in the previous slide. If you remember the previous slide where we said that a point and a plane will have 2 degrees of freedom. Here it's written. So this is a point, and if it's a 2D plane, then degrees of freedom will be 2 of this point. So similarly we are using same thing here. So we said that we have a point A on the coin, and we are not considering other points, okay, only point A. Only point A will have 2 degrees of freedom and no constraints. If we add one more point B at a distance DAB along with point A, now there are 2 points. Point A was already there, and we have added one more point, which is point B. So now we have one constraint, which is distance DAB, because it's a coin is a rigid body, and we have 1 degree of freedom, which is a rotation along this black circle. Similarly, if we add one other point along with point A, B, we add one more point, which is point C. So what happens? This point will have 2 constraints, 2 distances. Here I think I forgot to mention what are the constraints. Yes, so let's mention here. Two constraints, which is DAB and not AB, it's DBC and DAC. So these 2 constraints we have, and it has 0 degrees of freedom. Okay, so now let's drive an equation that tells us the total degrees of freedom of all these points on the coin, or degrees of freedom of a coin. So we can say that degrees of freedom of coin is equal to, we have sum of freedom of points minus number of constraints. So sum of freedom of points, or we can also write sum of constraints. Okay, sum of the total constraints you have. So degrees of freedom of coin is equal to, can say, sum of freedom of points minus sum of constraints of points. So this is how we calculate the total degrees of freedom of a rigid body in a 2D plane. So if you apply this equation to our coin, so we can say that we can add it here like freedom of point A plus degrees of freedom of point B plus degrees of freedom of point C minus constraints of point A plus constraints of point B plus constraints of point C. So from here we can say that freedom of point A, how many degrees of freedom it has 2 degrees of freedom. Okay, so point A has 2 degrees of freedom, and then point B has 1 degree of freedom, which is theta. Okay, here actually this freedom of points, its original freedom, not after subtraction. So here we have a little bit, we need to clear that. So remember when we pointed out here the freedom of point A, we said it has 2 degrees of freedom and 0 constraints. But for B, what we did, B originally had 2 freedoms because it's also a dimensionless point. It has 2 degrees of freedom, but after subtracting 1 constraint, it has 1 degree of freedom. Okay, so here, so it means that here we have to write the original freedoms, not after subtraction, because here we are subtracting here again. So we have to write the original freedom of the points. So if there are no constraints subtracted, then A will have 2 degrees of freedom, B will also have 2 degrees of freedom, and point C, this will also have 2 degrees of freedom, because we are not subtracting the constraints. Here when we said that point C has 0 constraints, 0 degrees of freedom, this was after subtraction. So 2 freedoms minus 2 constraints, 0 degrees of freedom. Okay, so that's why we are writing here the original freedom of points. So minus, now constraints for point A has 0 constraints. constraints for point B. Point B has one constraint, which is DAB. So we can write here 1 plus point C. It has two constraints, which are BC and DAC. So we can write down here 2. Now we have to just sum them all, and it will be 6 minus, and if we sum this one also, and this is 3. So if we add them, we have 3. So it means that this coin on a table will have 3 degrees of freedom. So we have developed a kind of method now that we can use to find the degrees of freedom of different rigid bodies, and this is same. The answer is same as we have in the previous slide, that we said that a coin will have 3 degrees of freedom. Here 2 degrees of freedom are the translations along x and y axis, and 1 rotation, so 3 degrees of freedom. So yeah, so this is a method that's useful if you want to find the degrees of freedom of complex rigid bodies. You can use this method, and yeah. So okay, so this is clear now, and now let's see how we can apply this method that we have already developed, and how we can use this method to find degrees of freedom in 3D, degrees of freedom of a coin in 3D. Okay, so okay, so here what we have to do is, we want to find degrees of freedom of a coin in 3D. So this is the problem. So let's make a (3D) axis So here we have z-axis, and then here we have the x-axis, and this is y-axis. So this is the axis, and now we're gonna make the coin here. Let's make it with blue. Okay, so this is a coin, and we take also the points that we did like last time. This is point A, and this is, here we have point B, and then we have point C here. So the distance between them, this is, you can call it DAB, this one is DBC, and this one is DHC. Okay, so now let's apply the same method that we applied in the previous slide, and let's see that this method works here, or what are the results. So if we want to find the degrees of freedom of point A, this is equal to, so this will be equal to the number of freedoms of point A. So remember, this is now a 3D. So in a 3D, as we have already discussed, that in a 2D a point can have 2 degrees of freedom, and in a 3D world, so I forgot to mention here, in a 2D world y and x, in a 2D world a point has two degrees of freedom, okay, but in a 3D world a point has 3 degrees of freedom. So this is the difference we have here. So since now we have a 3D world, so each point will have 3 degrees of freedom. So applying this same formula that we developed here, which was sum of freedom of points minus sum of constraints. So we shall apply same formula here also. So sum of freedom of points, degrees of freedom, is equal to sum of freedom of points minus sum of constraints. Okay, this is becoming a little bit minus sum of constraints of points. Okay, so for point A, this time we have point A has 3 degrees of freedom, plus point B has 3 degrees of freedom, plus point C has 3 degrees of freedom, minus, so for point, the number of constraints, because B has one constraint, which is which is a fixed distance from point A. So it has, sorry, the point starting from point A has zero constraint because it can move. If it's only a single point, it can go anywhere in this 3D world. Okay, so it has zero constraints. Plus point B has only one constraint, which is the distance from point A. So we add here 1. Now point C has two constraints, which is a fixed distance from point B and a fixed distance from point A. So it has two constraints. Now let's add 2 here. So if we add them, this is 9 minus 3. So if we, this will be 6. So degrees of freedom six. So it means that a coin in a 3D space will have 6 degrees of freedom. So now let's try to visualize where these 6 degrees of freedom are. So of course now you can see that the point, this coin can move along z-axis, it can move along x-axis and y-axis. Okay, and it can also rotate about x-axis, y-axis and z-axis. So here it's going. So these 3 degrees of freedom will be translation, so translation along x, y, z axis. And rotation about x, y, z axis. So this will be, the rotation can be described as theta and let's say alpha and beta. So these 3 rotations. So the total degrees of freedom will be x, y, z, theta, alpha and beta, where theta is the rotation about z-axis, alpha is the rotation about x-axis and beta is the rotation about y-axis. So I write down here also the rotations about I don't know, sometimes it doesn't work, it just gets stuck. Okay, so here rotation about z-axis we call it theta, rotation of about x-axis call it alpha, and rotation about y-axis we call it beta. So the degree of freedom, it has 6 degrees of freedom, the coin in 3D, in which there are 3 translations and 3 rotations. Okay, so now we have completed the degrees of freedom of a rigid body. So now let's see how we can find the degrees of freedom of different joints. In the first lecture we have already talked about the degrees of freedom of these joints, and so now let's revise once again and let's see how we can define the degrees of freedom of these joints considering the constraints also. So for the Revolute joint, we have, so it looks like something like this. So let's say here we have a Revolute joint here, and this is link 1 and this is link 2. And so if you see that in 2D, this is a 2D, okay? In 2D, there are two constraints. It cannot move along x-axis and it cannot also move along y-axis. So these two are the constraints. The only rotation here is allowed is the angle theta, which is the rotation about z-axis. So it means in 2D it has two constraints, and in 3D, if you look at 3D, it means it cannot move along x-axis, it cannot move along y-axis, also it cannot move along the z-axis. There is no translation along any of these axes. Also there is no rotation about x-axis, there is no rotation about y-axis, only the rotation is about z-axis, which is theta. So that's why it has 5 constraints in 3D and 2 constraints in 3D, and the total degree of freedom is 1. Now let's see prismatic joint. So for prismatic joint, we said that it looks something like this. And from here, okay, so it looks something like this. So similarly, prismatic joint, if you look in 2D, in 2D it will be, so this is a 3D version actually, this is a 3D version I made, and in 3D you can see that if I draw the axis here, let's say this is the x-axis, this is the z-axis, and this is y-axis. This is y-axis. So you can see that only there is translation about x-axis. This rod can move in and out, but there is no translation about z-axis, no translation about y-axis. So, and also there is no rotation about any of the axes. So it means that in 3D it will have how many constraints? It will have 5 constraints and 1 degree of freedom, which is translation about x-axis. In 2D, if you see in 2D we have, it will look like this. So in 2D, it can move along x-axis, but it cannot move along y-axis, and also it cannot rotate about z-axis. So there is no rotation. So it has only 1 degree of freedom. Similarly, a cylindrical, if you look at a cylindrical joint, so a cylindrical joint, it will have in 3D, it will look like something like this. So if you see let's say this is x-axis, this is so this is your z-axis here, and this is y-axis. So you see that this type of joint, it can have translation motion about x-axis and also a rotation about x-axis. It can rotate here, and also it can have translation motion about x-axis. But how many in 3D? If this is a 3D, in 3D it has how many constraints? It cannot move along z-axis or y-axis, and also there is no rotation about these two axes. So it should have 4 constraints in 3D, and it should also have, if you're looking at 2D, then it must have in 2D it cannot move, it can move along x-axis, but it cannot move along y-axis, and it cannot rotate about z-axis, but it can rotate about x-axis. So here also, you see, this has a motion like this, to and fro about x-axis, and also a rotation about x-axis. So it has 1 constraint, so in 2D it must have, okay, in 2D we don't have actually the z-axis. The z-axis is not there actually. So it can move along x-axis and also rotate about x-axis, but it cannot move along y-axis. So in 2D it has 1 constraint, and the degree of freedom will be 2. So let's see here. So here so this is correct, the 4 constraints in 3D, but in 2D it says that the constraints are not there and the degrees of freedom are 2. So it means that So here I have a doubt here, because what I remember is that in 2D these constraints don't exist for cylindrical joint, and the reason is that yeah, now I remember, because in 2D there can be no rotation about x-axis. Okay, there can be rotation about z-axis, but there can be no rotation about x-axis. So then it's not a 2D. So 2D means it's on a paper, it's on a screen, and any type of rotation, it must be along z-axis. Okay, not about x-axis. Then it's not a 2D. So here I made a mistake. So this is not correct. So this is a 2D version. It can only move actually forward, backward, but we cannot describe its movement along the rotation about the x-axis. So we simply say that it doesn't exist. We cannot calculate actually the constraints in the 2D. So that's why we can say that it's not calculatable. So just write down not applicable. And similarly for a universal joint and spherical joint. For a universal joint, it's difficult to draw, but you can tell that in a 3D it will have 4 constraints, and because it has 2 degrees of freedom, it means that it can rotate about any 2 axes. Universal joint can have rotation about any 2 axes, let's say x, y, and z. So it can let's say rotate about these 2 axes. Let's say rotation about x-axis and also rotation about z-axis. So there are 2 rotations, theta 1 and theta 2. If you want to see the figure of this universal joint, just go for the lecture 1, there you will find. It's very difficult to draw. So I'm just drawing the axis here. So it has 2 degrees of freedom, but it cannot have any translation about 3 axes. So 3 degrees of freedom, 3 constraints are there, and also it has no translation about 1 axis, so 4 constraints. And in 2D, it's not. In 2D, actually not applicable. So we can write down here for universal joint, the constraint doesn't exist. Because this joint actually, the universal joint cannot exist in 2D. Okay, and same is true for, I think, for cylindrical joint also. It cannot be shown properly in 2D. Okay, now the last one is spherical joint. So for spherical joint, if we see its axis, we have rotation about x, z, y. So we have a rotation about x-axis, a rotation about z-axis, and also a rotation about y-axis. So we can describe it theta 1, theta 2, and theta 3. So we have 3 rotations, but it means it has 3 degrees of freedom, but there is no translation about any of these axes, so there will be 3 constraints. And this is a 3D, and in 2D this joint cannot be represented, so not applicable. So yeah, so in 3D we have 3 constraints: the translation motion about x, y, and z axis. In 2D it's not applicable, and there are 3 degrees of freedom, which are the 3 rotations. So yeah, that's how we calculate the degrees of freedom of different joints. And let's quickly move toward our next slide. And now we shall try to calculate the degrees of freedom of more complex structures and mechanisms that we use in the robot. So for that we have a formula for that, and this formula is called Grubler's formula, and it is used to calculate the degrees of freedom of a robot. It is used to calculate degrees of freedom of robot. Okay, so what this formula is? This formula says that degree of freedom is equal to m n minus 1 minus sum of I is equal to 1 to j ci. So I will tell what is m and what is n and what's all about this other parameters that are being used here. So here when we write down here, m is number of freedoms of rigid body, where m is the number of freedoms of rigid body. And keep in mind that for planar, or you can say 2D bodies, the value of m will be always equal to 3. Okay, but for spatial or 3D bodies, value of m will be always be 6. So this is m, so number of freedoms of the rigid body. Okay, now we have one more parameter, it's called n. So what is n? N is the number of links. N is the number of links. Okay, and j is the number of joints. and C is the number of constraints. And the last one, so this formula can be further simplified. I will show you how we can simplify this. So if you remember, we in the previous slides we have tried to find the degrees of freedom in which we set the sum of the freedom of points minus sum of the number of constraints. Okay, so this is almost similar formula, but it's a little bit modified, but it's same that we used previously, like here, like this one here. Degrees of freedom of a coin, sum of freedom of points minus sum of constraints. So here we have also same thing, similar thing we have. So this formula can be further simplified by, it can be written as degree of freedom m n minus 1 minus j plus sum of I is equal to 1 to j f of I. So here what we have here, f is the freedom of joints. So this is how you can use either this formula or this formula, whatever you like. So I prefer using this one, modified one, but you can use this one also. So this formula we shall use to calculate the degrees of freedom of a robot, where m is the number of freedom of rigid bodies. For planar 2D, it will be, the value will be always be 3, and for 3D bodies it will be 6. And then n is the number of links of the robot, and j is the number of joints it has, and c is the number of constraints. So with the help of example we shall make it more clear that how it works. Okay, so let's see a small example. So in this example we have here, we have a robot which is the looks something like this. Okay, it has this robot. It has 1, 2, 3, 4 joints. I will mention the joints. And joint J1, and all are the Revolute joints. J2, J3, and J4. So this robot has 4 joints. And how many links it has? It has 1, 2, 3, link 1, link 2, link 3, or should I write the link below? Link 1, link 2, and link 3. And then we have one link here, this one, because this is fixed on the ground and this is also fixed on the ground. So both are when fixed to the ground, so it also represents one link. So we can call this as L4. So this robot has 4 links and also 4 joints. Okay, so now we have to calculate its degrees of freedom using Grubler's formula. So calculate the degrees of freedom of the instead of saying it robot, let's call it a mechanism. Or better call it closed chain mechanism. Using Grubler's formula. Okay, so this is our problem, and just to define what is closed chain, what is a closed chain. So closed chain means closed chain mechanism are the mechanism which has one or more closed loops. So I write down here, I think with blue or with green. Okay, so closed chain mechanisms have one or more closed loops. So why I'm saying it's closed loop? Because it started from a fixed ground and connected by links and joints, and then it came back to ground. So this is a closed loop. So if you imagine a ground also a link, then all the links are end-to-end connected. So that's why they're called closed chain mechanisms. So our problem is that we have to calculate the degrees of freedom of this closed chain mechanism using Grubler's formula. So let's see how we can do that. So according to the Grubler's formula, the degree of freedom is equal to m n minus 1 minus j plus f of I. So here in this case m is equal to, because this is a 2D a 2D mechanism. So for 2D mechanism, this M will be 3, number of, and N is the number of links. So we have here L1, L2, L3 and L4. We have 4 links, minus 1 minus joints. J is the joints. We have 1, 2, 3, 4. 4 joints plus, and now F is the freedom of each joint. Okay, degrees of freedom of each joint, F. So we know that for a revolute joint, for revolute joint, the freedom or degree of freedom is equal to 1, and that is theta. Or I think 1 is enough, is equal to 1. So in this case we have how many joints we have? 4 joints, and each joint has a freedom of 1. So we get something like this. This term will become minus 3 plus 4. We can make a line here so that the total degree of freedom will be 1 for this closed loop mechanism. So this is how we calculate the degrees of freedom of mechanisms. This example used a closed loop mechanism, but we can also calculate the degrees of freedom of an open loop mechanism using same formula. Just you need to keep in mind, if it's a 2D, you have to put here M will be equal to 3. If it's a 3D, then M will be 6. And F is the freedom of individual joint of single joint. For a single revolute joint, it has 1 degree of freedom, and so because of this summation, we have to sum up all the freedoms of J joints. In this case, we have 4 joints, so it will be 4 submissions. So final result is 1. So this is how we calculate degrees of freedom, and we can also, now let's calculate the degrees of freedom of an open loop mechanism. Open chain mechanism. Okay, so let's see how we can do that. So let's take an example of let's say we have a open chain mechanism or a 5-link robot. So here we can do that. This is the base link here, and then a joint, Revolute joint. This is link 1, and then again a joint. This is link 2, and then a joint. 1, 2, 3, and then we have link 4, and finally we have link 5. Okay, just to mention, this is link 1, link 2, link 3, link 4, and link 5. So we have 5 links here. And if you want to mention the joints, this is J1, J2, J3, J4. So it has 4 joints and 5 links. And we can call this, we can call it as either open chain, mechanism, or we can also call it 4R robotic arm, because it has 4 Revolute joints. So whatever you want, you can call it. Now the thing is, the problem is that we have to calculate the degrees of freedom of open chain mechanism given in figure below. Okay, so the first thing we do that we write down this Grubler's formula, and it says that degrees of freedom is equal to m n minus 1 minus j plus freedom of joints. So in this case we have m will be, because this is a 2D planar robot, so we use m is equal to 3, and number of links are 5, minus 1 minus number of joints are 4 plus, and sum of the freedom of each joint. In case of Revolute joint we have 1 degrees of freedom, so 1 plus 1 plus 1 plus 1, so this will be equal to this will be 0 plus 4, so the answer will be 4. So it means the degrees of freedom of an open loop, open chain mechanism, they are equal to number of joints it has, number of the revolute joints. If revolute joints are being used, so degrees of freedom will be equal to number of revolute joints. So this is an open chain mechanism. So you can also, here you can know that what is an open chain mechanism. So an open chain mechanism, also they are called serial mechanisms, and they do not have any closed loop. We can write down here open chain mechanisms are also known as serial mechanisms. They do not have any closed loops. So this is an example of open chain mechanism, and that's how we can calculate its degrees of freedom. Now let's have one more example, so we can completely understand how to calculate the degrees of freedom of a mechanism or a robot using Grubler's formula. So in this case we call it calculate the degrees of freedom of the closed chain mechanism given in the figure below. Okay, the mechanism looks like this. So we have here a fixed link here, and then a revolute joint here, and then we have a link, a second link, and then we have again a joint which connects this second link to a third link. And here we have one more link, but this time this link is the prismatic link here. Sorry, this joint is prismatic joint. Okay, so now total we have to calculate how many links we have total here. Um, Okay, so writing down the first of all the links. So here you can say this is the uh, fixed link, and this is a closed loop because this is also fixed on the ground, and here this link is also fixed to the ground. So we can call this as a closed loop mechanism, and this is our link 1, and then link 2, link 3, and finally we have a link 4 here. Or yes, I think this is correct one. And to number the joints, we have here the joint 1, which is a Revolute joint, and then we have joint 2, which is again a Revolute joint, and then we have here the joint 3. This is the joint 3, and this is again a Revolute joint, and then we have one more joint, that's a Rotary joint. We call it J4. Revolute joint, it's the Prismatic joint. So just to show you how this is a Rotary joint here, Revolute joint. This is Revolute joint. This is again a Revolute joint, but this link 4, L4, it can move left and right. So you can call it, it can move along x-axis. So it can move along x-axis. So we can call it as that this joint is a prismatic joint. It's better if we do like this. Okay. So yeah, so we have four links, and also we have here 4 joints. So now we have to calculate the degrees of freedom of this mechanism. Just by looking at it, can you tell what are the degrees of freedom of this robot? I think it's just by looking, it's a little bit difficult. So let's apply the Grubler's formula. It says that degree of freedom is equal to m n minus 1 minus j plus freedom of joints. So here in this case we have, you can say, Revolute joints. How many? We have 3 Revolute joints. Then we have prismatic joint, one. So in this case we have number of joints total, we have how many? 4. And we have number of links is equal to also 4. And since this is a 2D diagram, 2D representation of the mechanism. So in this case, M will be equal to 3. So once you have found these parameters, now just you have to put the values here, and 4 minus 1 minus 4 plus, so each joint has the Revolute joint has a degree of freedom of 1, so we can write here as 1 plus 1 plus 1 plus also the prismatic joint. It has also degree of freedom of 1, which is along x-axis, so 1. So here it will be this will become minus 3, and plus this will become 4, and the answer will be 1. So the degrees of freedom of this mechanism, this closed chain mechanism, is 1. So yeah, so I hope that now it is clear that how to find the degrees of freedom of closed chain and open chain mechanisms. Okay. Okay, now let's take an example, another example of finding degrees of freedom of a robot. But in this case, we can take an example of a delta robot. So the problem is find the degrees of freedom of delta robot given in the figure below. So here we have a delta robot in which we know that this delta robot, it has a base on top of it, where all the links are attached, and then it has here a revolute joint here. So make a revolute joint here, and this is attached to again here a revolute joint. This revolute joint is attached to a spherical joint here. I make the spherical joint darker to distinguish it from the revolute joint. Okay, and then we have here the on the lower end, on the end effector side, we have one more plate, and it looks like something like this. Okay, so here also we have a revolute joint. So I made a revolute joint here, and then we have here a link which is attached to a spherical joint, and on other side also a spherical joint. And now these two spherical joints are also connected by a link. And similarly the other side also. And we can repeat this process for other sides also. For example, here also you can do like this: a revolute joint, spherical joint, and then here we have a revolute joint, spherical joint here, and then we just connect them. And similarly here also we have one Revolute joint, a Spherical joint, again a Spherical joint, and they are also connected to the back side of this platform. So this is how, and in the end effector side we have attached some kind of tool like a gripper or something to grab objects here. So that's how this Delta robot structure is. And if you notice that how many links we have here, counting this one, this is the base link, and we can call it L1, and this is the second link, L2, and this is the third link, we call it L3. Okay, let's do like this: L3, L4, L5, and this is L6. Better if we do it this way, right? We call this one L1, and then we have L2 here, L3, L4, and L5 here. So this is for one arm. So there are three pairs of these arms. So in single arm we have 5 links. So in all these 3 arms we have how many links? 15 links on the arms, and this is you can call it L16, and this one L17, because it also connects different joints with each other. So this is also a link, and same is true for here. So here we have in total we have 16 links. So in this case we can write down n is equal to 16. Now let's see how many joints we have. For joints we can start here. This is J1, which is a Revolute joint, J2, J3, J4, J5, J6. We missed this middle one here. J2, J3, J4. This is a Revolute joint again, and then J5, J6, and J7. So on the one arm we have 7 joints, and 3 of the arms combined, they will have how many joints? 21. So yeah, so once we have the joints and links, I think then it's easier to find the degrees of freedom. So and keep in mind that this is a 3D. This whole is a 3D Delta robot. It's a 3D representation. So to find the To find the degrees of freedom, we use Grubler's formula, which says that degrees of freedom is equal to m n minus 1 minus j plus freedom of each joint. So in this case, we have here, we can say that in this case, because it's a 3D representation of delta robot, so in this case m will be equal to 6. Okay, so we write down here m is equal to 6, and number of links are 17 minus 1 minus number of joints are 21 plus, and so this is the sum of the freedom of each joint we have here. So how many joints we have here? We have two types of joints. One is a Revolute joint, second is the Spherical joint. So if you calculate the Revolute joints, we have 1, 2, 3 on the each arm, and 3 into 3 9. So we have total 9 Revolute joints here. So we write down here 9, and the freedom of each joint is 1. Okay, so because the Revolute joint, it has only 1 degrees of freedom. And that's theta, the rotation. So yeah, so we have written down here 9. Now plus, how many spherical joints we have here? 1, 2, 3, 4. 4 spherical joints. So it means so freedom for degrees of freedom of a spherical joint, they are 3, which are theta, alpha, beta, 3 rotation about the 3 axis. So we can write down here how many there were? 1, 2, 3, 4. Yeah, 4 on the each arm, and in the robot there will be 12. So it will be 12 spherical joints, and each has a degree of freedom of 3. If you solve them, you will get the answer 15. So it means that delta robot has 15 degrees of freedom. And the thing is, your end effector or the gripper, it will only have 3 degrees of freedom. Okay, this is because it can only move in X, Y, and Z directions. It cannot rotate, it cannot tilt, but it can only move along X, Y, and Z axis. I draw it here. X, Y, and Z. So the motion of this gripper will be along linear motions along X, Y, Z, but it cannot tilt, it cannot rotate. So that's why we can say that but the end effector gripper will only have 3 degrees of freedom, which are linear motion along x, y, and z axis. There is no tilt or rotational motion of end effector. So it means that if it has a 15 degrees of freedom but your end effector only has 3 degrees of freedom, so where are the other degrees of freedom? Where are they going? So the other degrees of freedom, if you minus 3 from 15, the other 12 degrees of freedom are called the internal degrees of freedom. So this is how we calculate the degrees of freedom of a 3D robot. I hope that this is clear, and yeah, so I think the time is over. We were not able to complete the next section, which is the configuration space, topology and representation, and I think we shall continue in the next lecture about this topics. So if you have any questions, you can contact me by email, or we can also have a Zoom meeting on every Sunday at 1 p.m. and there we can discuss, and if you have any questions you can ask there. So thank you very much for listening, and bye.